Hi, my name is Melissa. Today, our focus will be on the importance of Newton's second law, which clearly illustrates the relationships between initial and final velocities, the net force, time, and mass. In our case, we will focus on constant velocity with zero net force. So, have you ever wondered if a car moving on an interstate with its cruise control set to 70 miles per hour experiences a net force? Or have you wrongfully ever thought that zero net force means that the object just wasn't moving? In the next few minutes, we will discuss the concepts involved in the above questions, as well as go in depth with a real-world example involving a golf ball moving at a constant velocity with zero net force. With this example, you will find out why the experimental and model graphs and positions do not exactly match up, as well as the reason for the steady slopes on the graphs. So, the main physics idea is obviously Newton's second law and the momentum principle. In this law, which states the final velocity equals initial velocity plus net force divided by mass times the change in time, the idea of velocity relating to net force is strongly stressed. Since the change in time must be a positive number, and the mass has to be greater than zero, we are allowed to focus on the net force. We can also think of it another way. If the net force is zero, everything else is irrelevant because the whole part of the equation becomes zero. In addition, the momentum principle states how the change in momentum is equal to the net force times the change in time. Momentum is equal to mass times velocity, and since there is no change in momentum, velocity must stay constant. So now, after learning about the physics behind it, now let's put the physics into action. So below is a golf ball that's going to be rolled across the kitchen floor at a constant velocity. Now let's just see what happens. As you can note, I placed the center of the axis, the origin, in the center of the golf ball. As you can see, the dots are equally spaced apart. This means that it's moving at a constant velocity, as in, let's say, in each half a second, it's roughly moving the same exact distance. So now let's focus on the position versus time graph. As you can see, it is roughly a straight line. And as you know, the derivative of a position curve is the velocity curve. And as you can note with the mouse, the tangent line is roughly going to be the same all throughout. That means the slope is equal, which means the velocity is constant. But now let's ask a what-if question. So what if we flip the axis on the tracker software? If we would have done that, then the graph would simply just be flipped. The total displacement would be the same, it would just be in the opposite direction. So instead of the graph being like this, the graph would be like this in the fourth quadrant. So now, after we analyze the motion, now we're going to model it in Python. So we have to have the initial velocity. So in this case, we're going to do the change in position divided by the change in time. Here, we made the assumption that the initial velocity here using these values would, let's say, be the same using these values. This was important because the golf ball was supposed to be moving at a constant velocity. So therefore, we could in a sense pick any two values. Now let's look at important parts of the code. One important part is the initial position, which, because it's only moving along the x-axis, has this point, and the ball velocity, like I discussed earlier, is at that point. In addition, we made the F net vector equal to 0 because there is zero net force acting on the ball. Now let's see a comparison between the two graphs. As you can see, the model keeps the exact same slope throughout, which means the velocity was constant. However, in the experimental model, the slope gets less steep as we go on. This is due to friction and possibly the ball swerving since it was not in a straight line. So basically, the model that we did does not exactly predict the motion observed because it doesn't take in friction or the air resistance with the ball. So basically, you can't exactly pinpoint the total amount of pushes and pulls. We know friction, air resistance, and the initial forces were the main forces. However, other forces are still possible. So in conclusion, we can say because the initial velocity equals the final velocity, the net force must be zero.